Okay, I know I've beat this subject to death, but I'm going to keep doing it. So first, we have our feed wire here coming out of our power supply over here to this test light. This is our ground here to our power supply. You can see when I ground that, the light comes on. Okay, so I'm going to clip that back here and clip our ground back here. I have this test light also into ground here, and that goes over to our power supply. This probe here is our common or negative lead, or what I like to refer to as low reference. The reason I call this a low reference is because this is a voltmeter or a subtraction meter. All it ever does is measures the voltage at the positive lead and the voltage at the negative lead and subtracts the two to display a voltage. So knowing that this is my low reference, in this case I want this at the lowest point of voltage in the entire circuit, which is going to be at the ground at our power supply here. That's where I'm going to put that. So this is the positive lead on the meter, and you can see that reads right there, and I can touch that here, and you can see we have 12.61 volts, which is the same as our power supply. So it's putting out 12.61 volts, and if we check it here, we also have 12.61 volts because this is not grounded. We know it's not grounded because the light's not on. So if we have voltage feed here at our component, on the other side of our component, which is right here, we have 12.61 volts. Now, what I would like to demonstrate is what happens on a circuit that is working. So let's first make the circuit work. So the light's on. Now I'm going to take just my positive lead, because I have my low reference at the lowest point of assumed voltage, which is going to be at the negative at the battery or the negative at the power supply in this case. And then we're going to check throughout our circuit for the voltage we expect. Now this is a working circuit, so everything's going to work right? We're going to have 12.6 here, we're going to have 0 volts here, right? So let's check it. Well, we have 12.54 volts, not 12.6. What does that mean? Well, let's check over here. Well, we have 788 millivolts, not 0. What does that mean? Well, if I'm at a component and everything's working, do I even care that I'm missing, what do we got, 60 millivolts there, and we have almost 800 millivolts on our ground. Is that bad? Well, no, it's not bad because the light's lit, right? So I don't care, the component's working. So does it matter that we have that much voltage there? Obviously not, right? Because our component works. Well, what's happening? What we're seeing is this 12.54, and if I take this off, it goes up to 12.61, which is our battery voltage, right? What we're seeing is the resistance from here to here represented in voltage drop across here. Now, if we wanted to calculate the resistance from here to here, we would measure our voltage drop differently. Then I'm going to show you how we're going to do that. So I'm going to take this, my low reference now, because I know this point is lower than this point. So I'm going to take my low reference and set it here, and I'm going to take my positive lead and set it here. Well, now we've got about 60 millivolts of drop from there to there. So we have one part of our Ohm's law calculation, right? So we have about 60 millivolts, and you can see that changes, but we do know that, so we can measure that, and then we can calculate that if we know our current. Well, we do know our current because our voltage, or our display, tells us what our current is here on our power supply. So if I measure here to here, using my low reference on the lowest part of the voltage of this circuit that I want to test, and high at my battery positive, or my power supply positive, you can see that we're getting a voltage drop of 35 millivolts. And you can see sometimes that changes a little bit, and it's going to change as the circuit heats up, but you can see that drop on 282 milliamps of current. So now that we have our current and our voltage drop, we can calculate the exact resistance from the positive to the positive at our component. Why do we want to do that? I have no idea. I'm not building a circuit. I'm not an engineer. I don't care. I just want to fix broken stuff, right? So in the idea that I just want to fix the broken stuff, I'm going to put my low reference back at the lowest point in the entire circuit, which is going to be my power supply ground or my battery ground. Now I'm going to take my positive lead, and let's say I turn this on and it's not working. Well, okay, so I'm going to check for voltage at my component. I've got 12.6 volts. What does that tell me? Well, I know my battery voltage, if I check here, I have 12.61 volts. So what this tells me, by measuring exactly battery voltage at this component, it tells me there is no current flowing, and I have battery voltage at my component. All that tells me is I have continuity from the battery positive to my component right here, and that current is not flowing, because we know if current's flowing, this wire has some resistance and the voltage would be lower here. So since the voltage isn't lower here, we know current's not flowing, and we know we have a 12-volt supply, at least with some continuity to our component. Well, let's check our ground side of our component. Well, we have 12.61 here also. So what does that tell me? That tells me that we have a component that is not open because we have 12.6 volts here. It also tells me we have a ground that is open or has an extremely high resistance, because if we had a ground here, we would have less voltage. Not 0 volts, right? If we had 0 volts, then what would we have? Well, let's say we check at our component here, right? And we have, say 350 millivolts right here at our component. What does that mean? Well, if we check it here, we have 360 millivolts here. Well, what if we check it at our ground? Well, let's check it at our ground. I have 0 volts at our ground because there's no current flowing, right? And actually the voltage in this case is actually coming from this component here. So let's do ourselves a favor and bleed that off. So, oh, it's still not going to bleed off. So this actually has some capacitance, so you can see we do have a little bit of voltage there. Let's short that to ground and see if we can get this closer to 0. Yeah, alright, well, let's just skip that for now. We'll get the transistor out of the way. So now we have 0 volts here. So what happens if we're checking at our feed at our component, we have 0 volts? What does that tell you? That tells you that you have continuity to ground. That also tells you there's no current flowing, and you're missing your feed. But you do have continuity to ground, and how we can prove that is we have 0 volts right now at the feed side of our component. If we didn't have continuity to ground, and we just tested this, we're going to have some floating voltage. See how that's kind of going all over the place? So we have a few millivolts of just floating voltage naturally with nothing on this lead. The same if you're just holding your lead, you have just a random floating voltage. So I know if I have an open ground and I have an open feed or an open component, I may have a floating voltage. But that tells me something. That tells me we don't have continuity to ground and we don't have a feed. If we had continuity to ground, we would have zero, exactly zero, because the voltage here and the voltage here are identical. Clearly, there's zero difference between these two. So well, let's not even complicate anything. So now we know if we have a complete circuit to ground and we measured our feed side of our component, we have exactly 0 volts. It's safe to assume that our component has continuity through it. It's not open. And we have good continuity to ground here. And we're still just at our component. We're not going anywhere else in the circuit. We're not checking fuses. We're not doing anything else. We're just at our component with our component connected in the circuit. We have 0 volts here. We know we have an open feed, and we know we have continuity to ground. If we connect our feed, our light's going to light up, right? More than likely, because we don't have floating voltage on this. And now we have just under battery voltage, because we confirmed our battery voltage is 12.6, and we have just under battery voltage as we would expect on a working circuit. And then we're going to go here and check it, and we have 14 millivolts. And what that tells me is there's current flowing and we have a reasonably good ground, because we have 14 millivolts on that ground. We don't have 0. If we were to not have any current flowing, we wouldn't have 14 millivolts, we'd have 0, as we confirmed with as soon as we take off the feed, we can watch our voltage go to 0. The voltage goes to 0 because there is no current flowing, which means from here to the ground, the voltage difference is 0. And as soon as we connect this, the small amount of voltage drop from here to our battery ground or our power supply ground is 13 millivolts, or about 14 millivolts. What that tells me is there is some current flowing. So now we know if we check this component here and we have 14 millivolts, or we have some measured voltage that's extremely low, we know we probably have a ground with a good integrity, we have a working component, and we have feed. So we don't necessarily need to voltage drop end to end on the ground or the feed side. All we need is a known good point of reference, which in this case is 0 volts, because we're right at the ground on the battery or the power supply. And then we know if we're referencing 0, everything else is actual voltage. So now we can measure here, and we have an actual voltage at the feed of 12.59. If we measure at the battery, we have 12.6. So we have a small amount of voltage drop in the feed. But we don't care because it's reasonable. If we check this and it said 8 volts, that's not a small amount of voltage drop. We would have a dim light and we'd have a problem. In this case, we're going to check here. We have 14 millivolts and we have a good bright light, so we know that's an acceptable ground. We're not worried about that. So now let's add another variable. So now we have near battery voltage here, and we have battery voltage here. Because this component is not grounded, the feed is good. We know the component is not open because we have voltage here. Now we can check it here. On this side of the transistor, we have 0 volts. And what does that tell us? That tells us there's no current flowing from here to our battery ground. That also tells us that there is no open from here to the battery ground. If this was open, well, actually in this case, if this is open, we'd have voltage, because this is actually just a super high resistance. It's not actually open. So what that does is that proves the rest of this circuit is okay, because we're reading 0. Even though it's open, it's just okay. It's not guaranteed to be able to carry current flow. It's just okay. We know it's okay because we have 0 and no current flow. Now, when we introduce current flow by switching on this transistor, you can see our light's lit. We have some voltage drop here, not a whole lot, right? Just a little bit, because it's not 12.61, it's 12.59. And we check here, and we've got a few hundred millivolts. Is that acceptable? Well, you know, almost 800 millivolts, almost a volt. Is that acceptable? Well, yeah, our component works. I don't care that we have a little bit of extra resistance in that ground, because our component functions just fine. See? And then say we want to check here. Well, we've got 12 millivolts here. So now we know between here and here we have a what could be unreasonable amount of voltage drop depending on the current needed for your load. In this case, it's reasonable. We don't care. 800 millivolts sounds like a lot, but our component works, we're happy, and we can control our component by cycling the switch to ground on our transistor. And you can see that that carries basically no current, because that light only takes 40 milliamps to light, and it doesn't light. So we know we're just switching that on. And now we have 700 millivolts. We have we have 12 millivolts. And then if we check at our ground, which would be here, we have 0. So we know, by looking at this, we know current's flowing. We know we have some high resistance downstream, but not big enough to affect the way our component works. And we know that we're going to have some voltage drop across this transistor, and you can see that from here, from the 12 millivolts to the 800 millivolts. And we don't necessarily need to voltage drop from here to here to know that. We can just go here, well, we have almost 800. We go over here, well, we have 12 millivolts. We know the voltage drop is right here, and that's fine. We could calculate the internal resistance of this transistor if we wanted by moving our probe. So since we know this is the lower of the two voltages, we can put our low reference here and our high reference, or our positive, here, and we're going to see we have a voltage drop across that transistor of 770 millivolts. And now, since we know our current flow is 283 milliamps, we can calculate the working resistance of this transistor if we cared. We don't care, so we're going to move on with our lives and not waste time and energy. If you want to run that through your Ohm's law equation and figure out exactly what the working resistance of that is at 283 milliamps, feel free, right? But if we're just trying to fix broken cars, what we're looking for is what is making our component not function. Well, what does it take for the component to function? We need current, and we need a voltage differential. So we need a difference from here to here. Now, if we don't have a difference, which right now we clearly don't, we have 12.6 here and 12.6 here, what are we missing? Well, we need something to pull the voltage low, or we need something to make one side lower than the other in order to make this function. So, if we're checking at our ground side and our voltage matches our battery voltage, we know our component's likely good, we know we have a feed of some sort, and we know we don't have a good path to ground. And once we supply the good path to ground, our voltage gets lower, which gives us a difference between here and here, allowing current to flow, and that's what makes the light light, is the difference in voltage allows the current to flow. It takes the difference in voltage, or the voltage drop across the component, in order to allow the current to flow. So we need to know that there needs to be a difference. I don't need to know what the difference is. I don't even care. I don't care what the difference is. I need to know what this needs to work. If it's a 12-volt component, we need close to 12 volts across this component in order for it to work. So if I measure here with my ground, or with my negative lead on the ground, or my low reference on the ground, I measure here and I have 12.58 volts, and I measure here and I have 800 millivolts, my component's working because I have 12 volts across there, no problem. Now it's a little less than 12 volts, but do I care for a light bulb? Probably not. If this was a complaint where the light bulb was dim and I measured here and we had 800 millivolts, well, now we have a concern, right? We have this high resistance point and our light's a little dim. Well, what happens if we disconnect this and connect it directly to ground? So we have 800 millivolts here. See how bright the light is? Now let's connect it directly to ground. And now we have 12 millivolts here. And our light is slightly brighter. So now if this was a headlight bulb and we were complaining of dim headlights, we would try to find that 800 millivolts. In this case, though, we don't care. So again, component's not working. Say we have it grounded and the component's not working. You know, what do we have? We have negative voltage here. And we have negative voltage here. Well, that's weird, right? Well, we're getting our negative voltage from the voltage stored in this because this has some capacitance. So this is actually storing some voltage, and that's what we're seeing there. So if we eliminate the capacitance, which isn't always the case, because if you're testing a computer circuit, you might have that capacitance there and not understand that. Now you will, right? That maybe there's a transistor in the computer. And that's not typically the case, because this will actually have a circuit built into the circuit board to pull that voltage back down near zero. But now we have a direct path to ground. So we're going to check our voltage. We have near 0 volts here, basically 0 volts. So again, if we're checking at our component, and I check my feed with everything intact, and I have 0 volts here, that tells me something. It tells me that I don't have an open, because if I had an open, I'd have floating voltage. So I know I have a path to ground where I have my low reference in order for it to read and calculate 0 volts. That's really important to understand, because that could save you a whole lot of time just understanding when you have a floating circuit with an open, or you're reading an actual true 0 volts, as compared from here to here. Now, if you have this clipped on a body and you're reading 0 volts, all that tells you is you have 0 volts from here to here. It doesn't tell you that you have 0 volts from your battery negative. You have to actually be attached to your battery negative in order to get an accurate representation of the voltage in the circuit at this lead, because you have to be attached to the lowest point of voltage in the entire circuit, which is going to be your battery negative, or in this case, your power supply negative. So you can see that voltage is floating as soon as I touch it to the test light. Because it's grounded through this circuit and there's no current flowing, we get 0. Now, if there is current flowing, we would get something, right? And in this case, even with, because we're at the feed side, we have 12.53 volts, right? So I hate to keep hammering this to death, but I'm going to keep doing it to try to get this point across, that this is a very, very simple setup. I know it can be confusing, and I'm trying to make it not confusing, but if we check here, we have 800 millivolts. If we take the ground away, we have battery voltage. So even though we have 800 millivolts here, in this case, that 800 millivolts voltage drop from our component ground to our battery is acceptable in this case. It's not always acceptable depending on your component, but in this case it's fine. So it's just important to understand the relationship here. Now, I want to take a minute and show you on a graph why this matters. Let's change our time scale a little bit here. Let's go. Let's do that. Or config 200 points. Alright, so you can see with it just floating, it's kind of all over the place. Let me show you what real 0 looks like on the graph. Oops. That's showing you your negative voltage. So you see how real 0 is much flatter on the graph than floating. If it's floating, it's going to be a little all over the place. So if we're checking at 0, you see how it gets nice and smooth. And if I'm checking this at the component feed side and I have a nice flat 0, I know I'm probably have an okay ground, I probably have an okay component, and I'm just missing my feed. If I connect my feed to it, now we have 12.38 volts. If I remove my ground, oops, you see we gained a little bit of voltage. What we didn't really gain the voltage. What we lost was the voltage drop due to current flow across this feed circuit. So now we have battery voltage here. So we know if we check at our component and we have exactly battery voltage and we have a component that doesn't work, we know there's no current flowing. So now we have to decide, is the component open or is the ground missing? Well, I don't know. Let's go to the ground side of our component and check it. If we have exactly battery voltage there, what do we have? Well, we have a component that's not open and not grounded, because there's no difference between the ground and the feed side of the component. So now, if there is a difference, we can check that, and it's going to read about 12 millivolts. So you can see our ground isn't going to read 0 if there's current flowing. Our feed isn't going to read battery voltage if there's current flowing. If there's current flowing and everything's normal and your component's working, you're good to go. If you check here and you're down, say 20 millivolts, and you check here and you're up 20 millivolts, you know the circuit integrity is probably acceptable. If you're still having trouble with your component, it's probably just a faulty component. So again, if we have a computer-controlled circuit now, you can see that we have 12.61 volts here, and we have 12.61 volts here because there's no current flowing. Now, if we create a difference in voltage from here to here by activating our transistor, we can see that that gets pulled low. It doesn't get pulled all the way to 0 because that's impossible because there's current flowing. It would get pulled low to a reasonable voltage reading when referencing the lowest part of the circuit. So if your low reference is on battery ground or on the ground of your power supply, now we're showing about 800 millivolts there, but that's reasonable because that lights. And you can see when we take it away, the voltage goes high. This is how ground side drivers work in a computer, is when it's active, the ground is going to get pulled low. When it's not active, you're going to see near battery voltage or battery voltage at the component, depending on how it's fed. If it's fed through an ignition switch circuit with other loads, it's going to be lower because there's current flowing on part of that circuit, just not here. There's a lot of circuits ran in parallel on vehicles, and you'll see this voltage get pulled low sometimes when other components get turned on. So you can see here again, if I hold that on, we got battery voltage, and as soon as I turn the component on, our voltage goes down to our voltage drop from here to the battery ground, which in this case 800 millivolts is acceptable. So there's no problem with this circuit, the light's lit, everything's good to go. So I know this was a long video. Thanks for watching. I really appreciate it. I hope that hammering this to death like this really makes sense and really, helps fill in your knowledge of how a simple circuit works and what voltage drop testing is compared to how we use it in the field. When we're dealing with a broken component, we're not voltage dropping from here to here and from the battery positive to the component positive and from the battery negative to the component negative. We're not gonna do that. It's not very likely. More than likely what we're gonna do is we're gonna reference a known voltage, which is almost always gonna be your battery, because you have known battery voltage and known 0 volts. So if I put my low reference on 0 volts Now this can give me an actual representation of the voltage in the circuit based on a 0 volt reading on my low reference, because 12 volts minus 0 is still 12 volts, or 12.6 in this case. So when we're doing this, all we have to do then is check at our component. Do we have voltage here? Does it match battery voltage, or is it slightly lower? If it's slightly lower, there's current flowing somewhere in the circuit. Or you have an extremely high resistance. In some rare cases, you can have an extremely high resistance that will cause that voltage just to read low anyway. And that actually can be represented here. So we're reading 12.31 volts here. Well, there's no current flowing, and we know we have 12.6 volts for battery voltage. So this is low here with no current flowing. And it's important to understand that when you have extremely high resistances, that can happen. It's not very likely in automotive circuits, but it does happen. Actually, I ran into it the other day testing a solenoid. But it can happen. So it's important to understand when you're measuring this, what do you expect to see? And it's not always exactly battery voltage, and it's not always 0 volts. And all these little itty-bitty things that just seem like no big deal can help you be so much more efficient when you're diagnosing a problem. Because I could test at my ground and decide, well, if I have no feed and my ground reads 0, then I know I have a good ground within a reasonable amount. I know that I have good continuity between here and the ground. Now, until there's current flowing, I don't know how good this ground is or how much resistance is here, because even if I connect this here and touch it here, I still have 0 volts, even though it's through a component that clearly has resistance. So all I know is I have continuity. I don't know if it can carry a load, and that is where we're going to pay attention when we have this grounded and working. If I'm at my ground here and I'm reading 0 volts and I don't know if it can carry a load, and then I connect my component and my component lights, I am going to see some voltage here, and that's good. What that tells me is now I know that I have some voltage, and if I needed to, I could take a current measurement and then calculate the exact resistance of my ground under working conditions. Anyway, I hope this helps. If you like what you see, like, subscribe, share, ask any questions if you have any questions. Otherwise, I hope this helps kind of bolster your understanding of simple circuits, understanding voltage drop testing, and why we do it, well, I do it this way, and why I feel this is the most effective way to test most simple circuits.